Hello and welcome back to Calculus 1. We are finally at the fundamental theorem of calculus. How fundamental? Well, very fundamental, right? This is it. We are going to take the two concepts that are Calculus 1, which are derivatives and integrals, and just unite that, okay? So the fundamental theorem of calculus has two parts. Fundamental theorem of calculus is known as the Ftc, right? So Ftc Part 1 is the formula you already know, which is calculating definite integrals. So integral a to b of f of x dx is any antiderivative f of x computed from a to b, and then you get f of b minus f of a. So that is the first part of the fundamental theorem of calculus. You know how to compute this, so we don't dwell on that too long. It's the Ftc Part 2 that is interesting to us, and that is the following formula, and then we have to discuss this in detail. So ddx integral a to x f of t dt is equal to f of x. All right, so this formula here is the fundamental theorem of calculus part 2, and we are mainly going to focus on this now. Can anyone tell me what this formula essentially tells us? And you look at it, like, what is the core of this? What is it trying to say? Yes?
You add all the stuff to the tangent line and you get all these points. Never mind.
I mean, yeah, derivative, tangent line, all of that connected. There is something that it's much easier to derivative of sum equals f of x. If you were to rephrase that, I would take it as the answer that I'm looking for. What do you see over there? Wouldn't we just say that the derivative cancels the integral and just you have f of x? Yep. Now, yeah, that's technically what it says, right? These two guys are simply going to cancel each other out, and you're left, well, with the integral sign, this dies too, right? You just have that f of x is equal to itself. It's a lowercase f, right? The uppercase f is the antiderivative. So this is all we have. So now, if you look at this this thing, we can actually compute this, and this is pretty. I think this is the only foolproof that I do. No, I did some others, but let's compute this. So the derivative of the integral a to x of f of t dt. Now I'm using t as the variable. We can put any variable there; it doesn't matter. And when I integrate f of t, I'm going to get capital F of t. That's the antiderivative, right? And that antiderivative will be computed from a to x. Now, when I copy the derivative, now when I plug in this, I get f of x minus f of a. And now I have to take the derivative. Well, the derivative of antiderivative is the original thing, so you have f of x, and then derivative of f of a, that's a constant, so minus 0 is just f of x. It's a simple calculation that works out. That's a proof. as you can see, I integrated f of t, got the antiderivative f of t, that's capital, and when you differentiate that, you get f of x. So that's the proof. And now we can use this on a problem. Let's say you want to apply it on, let's go with t squared dt, so we are not from 3 to x. So we have d dx t cubed over 3 computed from 3 to x, which is, again, derivative of, and now you have x cubed over 3 minus 3 cubed over 3. This is the derivative of 1/3 x cubed minus 9. Well, derivative of 1/3 x cubed is 1/3 3x squared minus 0, which is x squared. We started with t squared, we ended up with x squared. So no matter what kind of a function is plugged in here, even those functions that you don't know how to integrate yet, like let's say ln x. ln x is a calc2 function. You know how to integrate 1 over x to get ln absolute x. But you don't know how to integrate ln t dt. That's a calc2 question. But if you see this in the setting of the fundamental theorem of calculus, you will just say, oh yeah, it's ln x. That's it, just move along. You literally Control C, Control V, and then you replace t with x and you're done. That's what it is. All right, good. Now, why is this so? Why is the derivative and this definite integral, why are they complete opposites of each other? Why are they canceling each other? Well, let's write the formulas for each and then look at those formulas and see what we can conclude. Again, this is a theoretical section. We don't have calculations past what you've seen. But let's consider the f prime of x is the limit h goes to 0 or f of x plus h minus f of x divided by h. And consider that the integral a to b of f of x dx is equal to the limit n goes to infinity, summation I goes from 1 to n of f of xi delta times delta x. Can anyone, looking at these two formulas, tell me why integrals and derivatives cancel each other out? Don't be shy. Why do they cancel each other out? Why are these opposite? Just employ the most basic thinking.
Come back to negative and one come back to that's the most basic.
Well, what do you mean one comes out negative, one comes positive? Well, it's it's as basic as that, but it's you just need to use what you see on the screen. We're not mentioning negative one. Go down to the place where you say what is opposite between these two, so that I can actually. One goes to 0, the other one goes to infinity. Okay, that's opposite. Good. What else? Thank you. One is division, one is multiplication. Perfect. That's completely opposite. What else? Well, that's what we are trying to prove, that it's opposite, and otherwise, if they're both integrals, then yeah. What else? So you picked up on the infinity and 0, and you picked up on division and multiplication. One more thing, or two more things, but one more that is obvious. Thank you. This one is subtracting, and this one is adding. Right? So most fundamental things that you just, by looking at it, just inspecting what the components of the formulas are. Derivative formula is a subtraction, this one is addition. Derivative formula is division, the integral one is multiplication. This one goes to 0, this one goes to infinity. And also there is this little tiny piece that pretty much no one ever notices. This is x plus h over here, and this is b minus a. There's that, right? There is as well, it's a little hidden thing. So yes, these are going to be completely opposite because all of the operations they have within them are opposite of what the other formula has. So yeah, they better undo each other. The last part, I'm just going to say that area under the curve and the value of the integral is not necessarily the same thing. So area under the curve is not always the same as the value of the definite integral. Again, make sure that the function is above x-axis for area calculation. So to find area, make sure f of x is positive on AB. Again, in parentheses. This is the same statement like in the previous I above x-axis. I mean, you can touch x-axis, obviously, but right. And that's that. That's the fundamental theorem of calculus. It connects our derivative with the integral, and then shows that they are completely opposite of each other. And you see that within the formulas. The fundamental theorem of calculus has two statements. Note that this one is using the antiderivative, right? And you compute upper minus lower. And this one is using the derivative of the integral. They eventually cancel, and they cancel because of the reasons we mentioned earlier. And that's that. I hope you're not disappointed, but you are responsible to know this statement for the final. It's one of the learning outcomes. If you are not able to list these two formulas and elaborate on what I have here on the screen at this moment, well, you are not achieving one of the, I believe, 6 learning outcomes of the course. If you look at your syllabus on the page 2, learning outcomes of the course is going to be your summary for the problems that are there in 2 days for the final. So fundamental theorem of calculus is a single lecture, which took us, what, 15, 20 minutes so far? And you know, it's like a sixth of your final exam. So yeah, make sure you know this stuff. All right, we'll restart for next one.